Far from the brightness of ordinary stars, there are objects that never quite became what gravity seemed to be building. They begin in clouds of gas and dust, inside the same cold regions where stars are born. Material gathers, the cloud contracts, pressure rises toward the center, and the young object grows warmer as gravity presses its matter inward. For a while, the process resembles the beginning of a star. Then the path changes. A true star eventually becomes dense and hot enough to sustain the fusion of ordinary hydrogen in its core. That steady reaction can continue for billions, and sometimes trillions, of years. It creates the long-lived inner furnace that allows a star to resist its own gravity and shine with a dependable source of energy. A brown dwarf does not cross that threshold. It may contain 13 times the mass of Jupiter, or 20 or 50 or more. Near the upper end of the range, it can approach the lightest true stars. Yet even with so much matter, compressed into a body roughly comparable in width to Jupiter, its core never settles into sustained hydrogen fusion. This does not mean that nothing happens inside. Some brown dwarfs briefly fuse deuterium, a heavier form of hydrogen, during their youth. The most massive may also burn lithium for a time. But these reactions are limited. They fade as their small supply of usable fuel is consumed, leaving the object without the enduring engine that powers a star like the Sun. What remains is heat. Heat from formation, heat from contraction, heat held deep within layers of hydrogen and helium, then released gradually into space. A young brown dwarf can glow warmly in infrared light. An older one cools, dims, and changes its atmosphere as centuries gather into millions of years and millions stretch into billions. To human eyes, many of these objects would be nearly invisible. Their name does not describe a true brown color because brown is not a single wavelength of light. Most of their radiation arrives beyond the red edge of ordinary vision, in the infrared, where warmer matter reveals itself without needing to shine like a star. Seen through the right instruments, a brown dwarf becomes a world of contrasts. It is born more like a star than a planet, yet it can have clouds, storms, winds, and weather. It may outweigh Jupiter dozens of times, while remaining close to Jupiter in size. Its interior is crushed by immense pressure, while its outer atmosphere may contain mineral clouds, salts, water, vapor, and molecules familiar from giant planets. It belongs to no simple category. Astronomers call it subarstellar, meaning below the mass required for a normal star. But that definition describes only what it cannot sustain. The deeper story is about what such an object becomes instead. A long-lived body cooling through the galaxy, carrying the memory of a stellar birth without the lasting fire of a star. Tonight, the journey will move across that narrow boundary. It will begin with collapsing clouds, pass through pressure and fusion, and continue into atmospheres where rock can become cloud, and weather can move across a surface that has no solid ground. It will follow the search for objects once predicted but unseen, and the instruments that finally found their faint signatures nearby. Brown dwarfs are sometimes called failed stars. But failure is a human word, and nature does not require every beginning to reach the same ending. Some objects simply stop at the threshold, then spend the age of the galaxy becoming something else. A brown dwarf begins before there is anything that could be called a surface. Inside a molecular cloud, gravity works on gas that is colder than any winter on Earth. The cloud is not uniform. It contains knots, filaments, ripples, and regions where matter has gathered a little more densely than elsewhere. When one of those regions becomes heavy enough, gravity begins to pull it inward. The collapse does not happen as a simple fall toward a single point. The cloud fragment turns as it contracts. Magnetic fields thread through it. Turbulence pushes some material aside, while other streams continue inward. Around the growing center, a flattened disk may appear, carrying gas and dust in broad orbits, while the young object gains mass. For a brown dwarf, the beginning can resemble the birth of a low-mass star. Observations of young brown dwarfs have revealed disks, jets, and signs of accretion, all familiar features of stellar infancy. This is one reason astronomers usually describe them as substellar objects rather than oversized planets. Their earliest structure is often shaped by the same cloud collapse process that creates stars, yet the smallest collapsing fragments are difficult to make. Gravity grows stronger as mass gathers, but gas pressure resists compression. Heat also matters. A fragment that warms too quickly can stop breaking into smaller pieces. For many years, astronomers debated whether a cloud could naturally produce an object only a few times heavier than Jupiter, or whether such low masses required a different route. Several possibilities remain under study. A small fragment may form inside a crowded stellar nursery, begin gathering material, and then be thrown outward through gravitational encounters before it has time to grow into a star. A disk around a young star may become unstable and divide, producing a companion whose mass lies in the brown dwarf range. In another case, radiation and winds from nearby massive stars may erode a forming core, reducing the material available to it. These paths are not mutually exclusive. Nature may use more than one. The important boundary is not a wall in space. It is a matter of how much mass the object keeps before its surroundings are dispersed, captured by a neighbor, or carried away. A little more material can move the center towards sustained hydrogen fusion. A little less can leave the object below that limit, destined to cool after its brief youth. As collapse continues, gravitational energy becomes heat. Particles fall inward, collide, and transfer motion into temperature. The center grows denser, pressure rises. The object becomes opaque enough that heat can no longer escape easily, and a compact interior begins to take shape. For a while, the young brown dwarf may look more star-like than it ever will again. It can be larger than Jupiter, brighter in infrared light, and wrapped in the remains of the cloud that formed it. Material from the disk may continue to fall onto its surface, releasing energy as it spins. Narrow jets can carry some matter away along the object's rotation axis. These outward streams may seem surprising, but they are part of the same balancing process seen around young stars, where infalling gas rotation, magnetic fields, and outflow all interact. Eventually, the surrounding supply diminishes, the disk thins, the envelope clears. The object is left with the mass it managed to collect, and that mass determines what the core can do next. Near the lower end of the brown dwarf range, the interior never becomes hot enough for significant nuclear burning. Higher mass brown dwarfs may fuse deuterium for a limited time. Deuterium is a rare, heavier form of hydrogen, carrying one proton and one neutron in its nucleus. It can begin fusing at lower temperatures than ordinary hydrogen, so it offers a temporary source of energy even when the main stellar reaction cannot continue. But the supply is small. Once the available deuterium has been consumed, the object returns to the slower release of heat left from formation and contraction. The heaviest brown dwarfs may also destroy lithium in their interiors. Astronomers can sometimes use the presence or absence of lithium in a spectrum as a clue to mass and age, because lower mass objects never become hot enough to burn it. Ordinary hydrogen is different. To sustain the long reaction that defines a main sequence star, the core must reach conditions that a brown dwarf cannot maintain. More mass would create stronger gravity, greater compression, and a hotter center. Without enough mass, the interior follows another physical path. As density rises, electrons are forced into increasingly restricted states. Quantum mechanics begins to resist further compression through a form of pressure known as electron degeneracy pressure. This pressure does not depend on heat in the same way ordinary gas pressure does. It allows the brown dwarf to support itself even as it cools. That change has a remarkable consequence. Adding more mass to a brown dwarf does not make it much wider. Stronger gravity compresses the interior more firmly, so objects across a broad range of brown dwarf masses can remain close to the size of Jupiter. One may contain several times the mass of another and still have a similar radius. The difference is hidden inside. The heavier object holds denser matter, stronger gravity, and a hotter core. The lighter one settles sooner into a cooler state. From a distance, they may both appear as small infrared points, but their interiors preserve the outcome of how much material arrived during those first uncertain stages of formation. There may have been a time when the night sky of a young star cluster held many such objects still wrapped in dust. Some remained beside the stars that formed with them. Some became companions in wide orbits. Others were scattered into the galaxy, carrying no parent star with them. They did not need to be stripped planets. Many may have been born alone, directly from fragments too small to become suns. A child looking into a dark sky would never notice them between the brighter stars. Their light is too faint for human eyes, and much of it lies in wavelengths we cannot see. Yet they may be present in the same nearby space, moving through the Milky Way with the ordinary patience of old objects. Their story was decided early, not by a sudden failure, and not by a flame that went out, but by the amount of matter gravity was able to gather before the nursery released them. Deep inside the young object, the question is no longer how it formed. The question is whether gravity can continue the work. As gas contracts, the center becomes hotter because falling material gives up gravitational energy. In a forming star, this process can raise the core temperature until hydrogen nuclei begin to combine. The reaction is difficult to start. Protons carry the same positive electric charge, so they repel one another. Only at high temperature and pressure can enough of them move close enough for fusion to proceed at a lasting rate. In the smallest true stars, this threshold is crossed only narrowly. They are cool by stellar standards, dim, red, and patient. Their cores burn hydrogen so slowly that they can remain active for far longer than the present age of the universe. A star near the lower mass limit does not shine because it possesses a large reserve of fuel alone. It shines because gravity's pressed that fuel just enough to begin a stable balance. A brown dwarf remains below that balance. Its center can become intensely hot and dense. It can briefly host nuclear reactions, yet the pressure created by its mass is not sufficient to maintain the ordinary hydrogen fusion that defines a true star. Before the necessary conditions can settle into place, the internal structure begins to resist further compression in another way. Electrons, which normally move through matter with a broad range of possible states, are forced closer together. Quantum mechanics prevents them from occupying identical states under the same conditions. As density increases, this restriction produces pressure even when the object is losing heat. This is electron degeneracy pressure. It does not ignite the brown dwarf. It supports it. The object can continue to contract for a time, but the contraction becomes less effective at raising the central temperature. The interior stiffens against gravity. The core approaches its hottest period, then begins a long decline. Instead of reaching a stable, hydrogen-burning life, the brown dwarf passes through a peak it cannot hold. This is the true meaning behind the phrase, "never ignited." It does not mean that the object was cold, inactive, or empty inside. A young brown dwarf may be hot enough to glow strongly in infrared light. Its core may reach temperatures of millions of degrees. Its atmosphere may radiate more energy than the object receives from any nearby star. But the central furnace never becomes self-sustaining. The difference between the heaviest brown dwarf and the lightest star can be a small fraction of the object's total mass. There is no single universal number that divides them under every condition. The exact boundary depends partly on chemical composition. Matter, containing different proportions of hydrogen, helium, and heavier elements, responds differently as it contracts. The details of the interior, including how efficiently heat moves outward, can shift the mass required for stable fusion. In broad terms, the dividing region lies near several dozen times the mass of Jupiter, close to about 75 or 80 Jupiter masses for objects with compositions similar to the Sun. Below it, a body is expected to cool like a brown dwarf. Above it, hydrogen fusion can become steady enough for the body to join the main sequence of stars. From the outside, that boundary can be difficult to recognize. A very young brown dwarf may appear brighter than an old low-mass star. Age changes luminosity because brown dwarfs fade continuously. A newly formed object can still hold much of the energy released during collapse, while an older one may have cooled for billions of years. Brightness alone cannot reveal whether the object is a star. Temperature also overlaps. Some old brown dwarfs can be cooler than a kitchen oven. Others, especially when young or massive, can reach temperatures comparable to the coolest stars. Their colors and spectra change as molecules form in their atmospheres. Clouds appear and disappear, and different gases absorb different wavelengths of light. Mass is the decisive quantity, but mass is rarely visible directly. Astronomers often infer it from motion. If a brown dwarf orbits another star, the gravitational effect on its companion can reveal how heavy it is. If two brown dwarfs orbit each other, careful measurements of their path and period can allow their masses to be calculated. In isolated objects, researchers must rely more heavily on temperature, luminosity, age estimates, atmospheric models, and the physics of cooling. This makes brown dwarfs difficult to classify with perfect confidence. Two objects with similar spectra may not have similar masses. One might be young and light, still warm from formation. Another might be older and heavier, with stronger gravity compressing its atmosphere. Their outward appearance can converge, even though their histories are different. The interior leaves clues, however. One of the most useful involves lithium. Lithium is a light element, but it is easier to destroy through fusion than ordinary hydrogen. The cores of the more massive brown dwarfs can become hot enough to consume it, while lower mass brown dwarfs cannot. Very low mass stars also destroy their original lithium during early stages of their lives. When astronomers detect lithium in the spectrum of a cool, faint object, its presence may indicate that the object never became hot enough inside to burn it. Under the right conditions, this can help distinguish a brown dwarf from a star. The method is not automatic. A young object may still retain lithium, even if it will eventually destroy it. Very low mass brown dwarf may preserve lithium indefinitely. Age and mass must be considered together. Still, the lithium test gave astronomers one of the first practical ways to confirm that some faint red objects were not merely small stars. Deuterium offers another boundary. It is a rare form of hydrogen whose nucleus contains a proton and a neutron. It fuses at lower temperatures than ordinary hydrogen. Objects above roughly 13 Jupiter masses can generally burn at least some of the deuterium they were born with, although the exact threshold also depends on composition and on how the object formed. This reaction does not last long enough to turn a brown dwarf into a star. The available deuterium is limited. Once it is consumed, the temporary support it provided fades. The object continues to cool. For a brief part of its youth, fusion may slow the contraction and alter the way its brightness changes, but it does not create a permanent main sequence state. A brown dwarf can therefore contain several different histories of nuclear activity. The smallest may never fuse anything at all. More massive examples may burn deuterium for a time. Heavier ones may also destroy lithium. yet all remain unable to maintain the ordinary hydrogen fusion that powers stars. The labels become less tidy near the lower end. A free, floating body with 5 or 10 times the mass of Jupiter may have formed through the collapse of a cloud, much like a star. Another object of the same mass may have formed inside a planetary disk and later been thrown into interstellar space. They could end with similar temperatures, similar atmospheres, and similar masses while arriving there by different paths. One might be called a planetary mass brown dwarf. Another might be called a rogue planet. The physics of the body does not change when the name changes. The uncertainty belongs to the history, not necessarily to the object standing before the telescope. Near the upper boundary, the same difficulty appears in another form. A brown dwarf, only slightly too light for hydrogen fusion, may look almost identical to a red dwarf star. Both can be small, cool, reddish in visible light, and brighter in infrared wavelengths. Both can have complex magnetic fields and active atmospheres. Their radii may be similar, but time separates them. The red dwarf continues to draw energy from hydrogen fusion. Its brightness can remain stable over spans far longer than human history. The brown dwarf has no comparable source. Every era carries it farther from the heat of its beginning. At first, the change may be difficult to notice. Over millions and billions of years, it becomes the central fact of the object's existence. It cools. Its internal energy leaks outward. Its atmosphere changes with the falling temperature. Molecules that could not survive in its youth begin to appear. Clouds form from materials that once remained vapor. Different layers become visible at different wavelengths. The object passes through a sequence of spectral identities, not because its mass is changing, but because its remaining warmth is leaving. A star spends most of its life sustaining a flame. A brown dwarf spends its life remembering compression. And from that slow release of stored heat, an entire hidden weather system begins to emerge. The weather begins where the solid surface never does. A brown dwarf is made mostly of hydrogen and helium, like a giant planet, and like the stars from which its material came. There is no ground beneath the clouds in the familiar sense. If you could descend through the atmosphere, the gas would simply become warmer, denser, and more compressed. What astronomers call the surface is only the level from which most of the observable light escapes. That level changes with wavelength. Infrared light at one color may emerge from high clouds, while another color reaches us from deeper and hotter layers. A telescope does not see one clean boundary. It receives a layered portrait with different parts of the atmosphere revealing themselves through different bands of light. In the warmer brown dwarfs, the clouds can be made from materials that would be rock or metal on Earth. Silicon-bearing minerals rise as vapor from the hotter depths. As that vapor moves upward and cools, it can condense into tiny grains. Iron can form droplets. Other minerals may join them. The clouds are carried through a rotating atmosphere above deeper layers, glowing with heat left from formation. The word cloud can sound familiar, but the conditions are not. Temperatures in these regions may be high enough to melt many terrestrial rocks. A grain of silica can form in one layer, fall into warmer gas, evaporate, rise again through mixing, and condense once more. The atmosphere becomes a continuing cycle of chemistry, motion, and heat. There may be rain, but not rain that reaches a surface. Particles grow heavy and settle downward. Some sink into hotter regions and disappear back into vapor. Others remain aloft longer, held by rising currents. This repeated settling and return can remove materials from the upper atmosphere and carry them deeper, changing which molecules remain visible above. A brown dwarf can therefore hide parts of its own chemistry. Elements may disappear from the upper layers after becoming locked inside clouds or falling below the region telescopes can easily probe. The spectrum depends not only on what the object contains, but on where that material has moved. The clouds are not expected to form one smooth, permanent blanket. Brown dwarfs rotate, often completing a turn in only a few hours. Their rapid spin can organize winds, shape bands, and stretch atmospheric features across large distances. Heat rising from below meets layers that radiate energy into space. Cloud particles absorb and scatter that radiation. The clouds alter the temperature around them, and the temperature changes the clouds in return. This feedback can produce an atmosphere that is always adjusting. One region may hold a thicker deck of mineral grains. Another may open into a thinner patch through which warmer layers become visible. As the brown dwarf turns, those regions rotate in and out of view. The object brightens slightly, then dims, not because its interior is changing, but because its weather is carrying different patterns across the side facing Earth. Astronomers can watch those changes as a light curve. They measure the brightness again and again. A repeating rise and fall can reveal the rotation period. Differences between infrared wavelengths can show whether one layer is changing before another. When the pattern evolves, it suggests that the clouds are moving, growing, breaking apart, or being replaced. No telescope can usually resolve the disk of a brown dwarf into a detailed photograph. Even a nearby one remains a tiny point, yet time can turn that point into a map. As changing regions rotate through view, their signatures can be separated mathematically. With enough measurements, astronomers can infer broad, bright and dark areas, temperature differences, and cloud structures. The result is not a direct image in the ordinary sense. It is a reconstruction from rhythm, color, and motion. The method resembles listening to a room from outside and learning where people are pausing by the way the sound changes. The room is never seen clearly, but movement leaves a pattern. Some of the strongest brightness variations appear near the transition between warmer L-type brown dwarfs and cooler T-type brown dwarfs. In the L dwarfs, thick mineral clouds strongly influence the light that escapes. As these objects cool into the T range, methane becomes more prominent, and the cloud layers may sink deeper, thin out, or break into patches. The precise details are still being studied. There may not be one universal transition that occurs in the same way for every object. Gravity, age, composition, rotation, and cloud particle size can all affect what happens. But the broad change is visible. The atmosphere becomes clearer in some infrared windows, allowing radiation from deeper and hotter layers to escape. A cooling object can briefly become brighter at certain wavelengths, even while losing energy overall. That seems backward until the clouds are considered. If a thick layer opens or settles lower, deeper heat can become easier to see. The brown dwarf has not begun producing more energy. The path outward has changed. Below the mineral clouds, the chemistry continues to shift. Carbon can be carried mainly in carbon monoxide at higher temperatures, and increasingly in methane as the atmosphere cools. Water vapor becomes prominent across much of the brown dwarf sequence. Ammonia appears more strongly in the coldest classes. Sodium and potassium can shape broad portions of the spectrum in warmer objects, while salts and sulfides may condense into clouds at lower temperatures. Each step downward in temperature changes the visible atmosphere. An older brown dwarf is not simply a dimmer version of its younger self. It can become spectrally different with new molecules, new cloud species, and new depths revealed to space. Its apparent identity changes as cooling moves chemical boundaries through the atmosphere. This is why astronomers use the letters L, T, and Y. The sequence is based on spectra rather than a single measurement of mass. L dwarfs are warm enough for metal hydrides, alkali atoms, and mineral clouds to shape their appearance. T dwarfs show strong methane absorption and often clearer views into deeper layers. Y dwarfs are colder still, with spectra affected by water, ammonia, and chemistry approaching giant planet temperatures. The letters describe what the light looks like now. They do not tell the whole history. A low-mass young object and a more massive old one can sometimes reach similar atmospheric temperatures. Both may receive the same spectral letter, while carrying very different gravity, density, and ages inside. The atmosphere preserves some of those differences. Higher gravity compresses the gas more strongly. Lower gravity can allow thicker clouds to remain aloft and can make a young object appear redder in infrared colors. Metal abundance changes, which condensates form and how strongly molecules absorb light. Rotation affects circulation. Magnetic fields can add another source of structure. A brown dwarf is not a simple cooling sphere. It is an atmosphere responding to an interior, a history, and a particular set of physical conditions. There are storms in these atmospheres, though the word storm must be used with care. Astronomers do not usually see a single cyclone with a sharp edge, as spacecraft have photographed on Jupiter. They detect large-scale disturbances through changing brightness and spectra. Some may be bands, some may be vortices, some may be broad regions of thick and thin cloud. The exact shapes remain uncertain. The winds may be powerful, driven by heat rising from the interior and organized by rapid rotation. Unlike a planet close to a star, an isolated brown dwarf does not need sunlight to power its weather. Its energy comes mainly from below. That makes it a useful natural laboratory. On Earth, weather is dominated by sunlight, heating the surface and atmosphere unevenly. On Jupiter and Saturn, sunlight and internal heat both matter. On a free-floating brown dwarf, external illumination may be negligible. Its weather grows mainly from stored heat moving outward. The distinction helps astronomers understand giant exoplanets as well. Young planets photographed far from their stars can have temperatures and atmospheres resembling low-mass brown dwarfs. Both may hold silicate clouds, carbon monoxide, methane, water vapor, and complex circulation. Brown dwarfs are often easier to observe because they can be isolated from the glare of a nearby star. What is learned from one class of object can guide the interpretation of the other. A cloud feature found in a brown dwarf spectrum may suggest where similar particles hide in a young giant planet. A model of atmospheric mixing can explain why carbon monoxide remains visible, where equilibrium chemistry would predict more methane. A measured rotation period can show how quickly weather patterns may cross an unseen disk. The light becomes a record of motion. There is another kind of activity as well. Some brown dwarfs produce radio emission. Some show signs of auroras, magnetic fields, and charged particles moving through their surroundings. These phenomena are not identical to the cloud weather, but they can occur above the same rotating atmosphere. In certain objects, radio pulses repeat with the rotation, like a distant beam sweeping past Earth. This reveals that a body without sustained hydrogen fusion can still be magnetically active. Rotation can help maintain a magnetic field. Currents can accelerate particles and deposit energy in the upper atmosphere. The resulting emission adds another layer to an object once expected to do little more than fade. Nothing about the brown dwarf is static. Clouds settle and return, molecules form, and are carried out of equilibrium. Bright regions move across the visible hemisphere. Magnetic signals pulse. Heat escapes from depths no telescope can directly enter. All of this happens on a body that may look from across several light years, like a faint and nearly featureless point. There is a familiar thread in the way people first learn weather. A child does not begin with equations for pressure or circulation. The first lessons come from noticing change. A darker cloud, a shift in wind, the smell before rain. The way afternoon light fades across a room. Pattern comes before explanation. Astronomers meet brown dwarf weather in much the same order. First comes the changing light, then the repeating period, then the realization that the point is turning. Only after that do the clouds begin to take shape in the mind, mineral grains suspended above deeper heat, openings that expose warmer layers, winds carrying chemistry around a world with no ground. The atmosphere cannot be visited, but it can be watched. Hour by hour, rotation brings another part of it forward, and in those small changes of infrared light, the unseen sky begins to move. For a long time, brown dwarfs existed more clearly in equations than in the sky. Astronomers understood that stars could not continue downward in mass without limit. A shrinking object needs enough gravity to compress its center until ordinary hydrogen fusion can support it. Below some threshold, the interior would become dense enough for quantum pressure to slow the contraction before the core could settle into a lasting stellar flame. The physics suggested that such objects should exist. Finding them was another matter. A brown dwarf could be smaller and dimmer than the faint red stars already difficult to observe. As it aged, most of its light would move into infrared wavelengths, beyond the range of the eye and beyond the strengthness of many early photographic surveys. It could pass through the solar neighborhood without announcing itself in visible light. The first searchers, therefore, faced a strange problem. Astronomers were looking for a predicted population whose appearance was not yet fully known. A candidate might be a very low-mass star, a distant red object altered by dust, or a young planet-like companion. Faintness alone was not enough. Across the following years, detectors improved. Infrared astronomy moved from a specialized frontier toward a practical way of surveying the sky. New instruments could record wavelengths where cool bodies release much of their energy. Larger telescopes collected more light, while electronic detectors allowed subtle signals to be measured with greater sensitivity. Young star clusters became useful places to look. Inside a cluster, many objects share roughly the same age and distance. That common setting makes comparison easier. If a faint candidate moves with the cluster and appears too cool and too dim to be an ordinary star, astronomers can estimate its place below the stellar boundary with more confidence. One of the decisive tests involved lithium. A very low-mass star becomes hot enough during its early life to destroy the lithium it was born with. A lower-mass brown dwarf may never reach that temperature. When lithium remains visible in the spectrum of a cool, faint object, it can show that the interior never became hot enough to follow the path of a true star. In the mid-1990s, this test helped confirm Tide 1, an object found in the Pleiades star cluster. Its faint light, its membership in the cluster, and the lithium preserved in its atmosphere placed it below the hydrogen burning limit. It was not merely a small red star. It belonged to the population that theory had anticipated. During the same period, another object provided a different kind of proof. It appeared beside the nearby red dwarf Gliese 229. The companion was faint in visible light, but detectable in infrared observations. Because it orbited a known star, astronomers could study its relationship to a system with a measured distance. The object became known as Gliese 229b. Its spectrum carried methane. That molecule was familiar in the atmospheres of giant planets such as Jupiter, but it was not expected to dominate the light of an ordinary star. Methane can survive in cooler atmospheric conditions, and its presence showed that this companion occupied a thermal world beyond the coolest known stars of the time. In 1995, observations of Gliese 229b were presented as the first unambiguous detection of a cool brown dwarf. Ground-based telescopes separated it from the glare of its host star, and the Hubble Space Telescope helped confirm the faint companion. The missing class had finally become visible. The discovery did more than add one object to a catalogue. It gave astronomers a spectrum to study, a real atmosphere to compare with models, and a target whose temperature could be placed between low-mass stars and giant planets. Theoretical predictions could now be tested against light arriving from an actual substellar body, and the light did not match every expectation. Gliese 229b was cooler and fainter than many early searchers had assumed brown dwarfs would be. Its methane-rich atmosphere showed that the path from star to planet was not a simple extension of red stellar color. New spectral categories would be needed. The familiar stellar sequence had once ended with M. M-type stars include the coolest ordinary stars, along with some young brown dwarfs that can resemble them. But as more substellar objects were found, their spectra revealed features that did not fit comfortably inside the old class. Dust and mineral clouds shaped some of them. Methane transformed others. Astronomers introduced the L class for objects cooler than most M dwarfs, where metal hydrides, alkali atoms, and suspended condensates alter the outgoing light. The T class followed, for cooler bodies, with strong methane absorption and atmospheric windows that expose deeper layers. These letters were not simply labels added to a filing system. They were evidence that cooling brown dwarfs move through a sequence of atmospheric states. The categories gave observers a shared language for chemistry, clouds, and temperature, even when the mass and age of an individual object remained uncertain. Wide surveys then changed the scale of the search. Instead of pointing a telescope toward one promising star or one young cluster, astronomers could examine broad regions of the sky for objects with unusual infrared colors. Surveys such as 2-micron All-Sky Survey and the Sloan Digital Sky Survey found large numbers of L and T dwarfs, turning a nearly empty category into a varied population. Some were companions to stars. Some traveled in pairs with other brown dwarfs. Many appeared alone. Their motion across the sky helped reveal which ones were nearby. A close object shifts position against distant background stars more noticeably over time. Images taken months or years apart can show that movement, allowing a faint point to separate itself from the fixed pattern behind it. The surveys found many brown dwarfs, but not enough to dominate the local population. They are common members of the galaxy without being the majority. The search moved toward colder objects. A brown dwarf that has cooled for billions of years may emit so little visible light that ordinary imaging offers almost nothing. At those temperatures, the best clues lie farther into the infrared, where the object's remaining heat can still be distinguished from space. NASA's Wide Field Infrared Survey Explorer scanned the entire sky in infrared wavelengths. Its observations uncovered large numbers of cool brown dwarfs and, in 2011, helped establish the Y class, colder than the known T dwarfs. Some had atmospheric temperatures approaching those of rooms, weather systems, and planets, rather than familiar stars. This changed the scale of the discovery. The first confirmed brown dwarfs had shown that objects could form like stars without sustaining stellar fusion. The Y dwarfs showed how far the cooling could continue. A body born in a collapsing cloud could age until its atmosphere was no warmer than many places on Earth. One nearby object, known as Y0855, was later found to be colder still, with an estimated temperature below the freezing point of water. Whether every object at such low mass formed like a brown dwarf or like a planet is not always clear. The atmosphere can be measured more easily than the forgotten circumstances of birth Earth. The sky surveys produced more data than professional teams could inspect alone. Citizen scientists began comparing infrared images from different years, looking for points that moved. Remains remarkably good at noticing motion within crowded fields, even when automated systems miss an object because it is faint, blended, or unusual in color. Through projects built around archival survey images, volunteers have helped identify new brown dwarf candidates and some of the coldest neighbors of the Sun. Their work follows the same basic clue used in earlier searches. A nearby object changes its position, while the distant sky remains nearly fixed. The search has therefore widened across generations of instruments and observers. A theoretical boundary became a faint companion beside a red star. A faint companion became a spectral class. A spectral class became an all-sky population. And an all-sky population became a way to study clouds, chemistry, magnetic fields, formation, and the difference between planets and stars. Even the first famous discovery did not remain simple. For decades, Gliese 229b appeared to be one brown dwarf whose measured mass and faint luminosity did not fit together comfortably. In 2024, observations with instruments on the Very Large Telescope resolved the puzzle. The object called Gliese 229b is itself a close pair, two brown dwarfs, orbiting one another so tightly that earlier telescopes had blended their light into a single point. The first clear example of the class had been carrying another hidden object all along. That revision is part of the same story as the discovery itself. Astronomy does not reveal a finished sky. It returns to familiar targets with sharper instruments, longer records, and new questions. An object can be known well enough to name, classify, and teach for 30 years, then change in meaning when one point of light separates into two. There is a generational thread in that work. The astronomers who predicted substellar objects did not have the detectors that would finally find them. The teams who confirmed the first examples could not yet conduct the deeper all-sky infrared surveys that followed. Later researchers inherited the early discoveries, tested them again, and found new structure inside the evidence. The objects waited through all of it. They cooled before the first telescope was built. They moved through the galaxy while photographic plates gathered starlight. They crossed infrared detectors as faint points, sometimes noticed at once, and sometimes found years later in stored observations. The search was never only for something dim, it was a search for a category nature had placed between familiar ones. Once brown dwarfs were found, the boundary between planet and star did not become sharper. It became more populated, more textured, and more difficult to reduce to a single line. The missing objects had entered the catalogue. Now, astronomers had to learn how many there were, where they lived, and what their numbers could reveal about the way the galaxy builds its smallest lights. The first discoveries answered one question and opened another. Brown dwarfs existed, but no one yet knew whether they were rare interruptions in the making of stars or a normal result of the same process that fills the galaxy with red dwarfs, binary systems, and wandering worlds. To learn that, astronomers had to count objects that were difficult to see. A census of ordinary stars can begin with visible light. Nearby stars reveal themselves through brightness, color, and motion. Brown dwarfs require a more patient inventory. The warmer examples may appear in deep optical surveys, but older and colder ones often emerge only in infrared images. Some are found because they move against the background sky. Others are recognized through spectra that show methane, water vapor, alkali metals, or the changing signatures of clouds. Every survey is incomplete in a different way. A telescope may be sensitive to warm brown dwarfs, but miss colder ones. A search designed to find isolated objects may overlook a faint companion beside a bright star. A color selection that works for one spectral class may exclude an unusual atmosphere with different gravity, chemistry, or cloud thickness. The missing objects must be estimated as carefully as the detected ones. Astronomers build models of what a survey could have seen, then compare that reach with what it actually found. The result is not a perfect count, but a gradually improving picture of the local population. That picture suggests that brown dwarfs are common, though less numerous than the smallest stars. They occupy the same neighborhoods, They move through the thin disk of the Milky Way. Some are young members of star-forming regions, still warm and bright from their beginnings. Others are old field objects that have traveled around the galaxy for billions of years, fading as they go. Their distribution carries information about formation. If brown dwarfs were made only through a rare accident, their numbers and surroundings might look sharply different from those of stars. Instead, many appear to continue the population of low-mass stars towards smaller masses. This supports the idea that direct collapse and fragmentation can produce objects below the hydrogen-burning limit. But the continuation is not perfectly smooth. Brown dwarfs also reveal patterns that suggest the smallest fragments do not form with unlimited ease. Gas must cool, separate, and avoid being gathered into a larger neighbor. In crowded nurseries, a small core may be disrupted or ejected. In disks, gravitational instability may create companions under some conditions, but not others. Different routes may overlap in the final census. Companions offer some of the clearest clues. A brown dwarf can orbit a star, another brown dwarf, or perhaps host lower mass companions of its own. The distance between the objects, the shape of the orbit, and the ratio of their masses preserve traces of how the system assembled. Wide companions can resemble members of a small stellar family. They may have formed from neighboring fragments in the same collapsing cloud, then remained loosely bound. Close companions may point toward fragmentation at smaller scales, migration through a disk, or gravitational interactions that tighten the orbit. There is no single arrangement. Some brown dwarfs circle stars at distances far beyond the outer planets of our solar system. Others lie much closer, though such systems show a notable pattern around stars like the Sun. At short orbital distances, brown dwarf companions are uncommon compared with both stellar companions and giant planets. This scarcity is known as the brown dwarf desert. The name does not mean that close brown dwarf companions never exist. They do. The desert describes a relative lack of them in a region of companion mass and orbital distance where other kinds of objects are found more often. The pattern is useful because planets and stars are not distributed around their hosts in the same way. Close giant planets can form in disks and later move inward. Stellar companions often arise from fragmentation of a larger cloud or collapsing system. Brown dwarfs lie between those mass ranges, but the processes that create and move companions do not necessarily fill the middle evenly. A disk may struggle to build an object tens of times heavier than Jupiter without the growing body opening gaps, redirecting gas, or becoming dynamically unstable. A collapsing cloud may more readily produce two objects with masses closer to one another than a sun-like star, paired with a much smaller brown dwarf. The desert may therefore reflect more than one formation boundary. It is not a clean verdict. Surveys find brown dwarfs in close orbits, and the details depend on the mass of the host star, the orbital period being examined, and the sensitivity of the search. Still, the broad shortage remains a clue that companion formation is shaped by more than available mass alone. Brown dwarf pairs provide another view. Many known binaries contain two components with fairly similar masses. Their separations are often modest compared with the wide range seen among ordinary stars. Very wide brown dwarf pairs exist, but they can be fragile. Passing stars, molecular clouds, and the gravitational environment of a young cluster can pull weakly bound systems apart. A close pair is harder to disrupt. Once discovered, such a binary becomes especially valuable. Its orbit reveals the total mass through gravity, rather than through uncertain cooling models. If the two objects can be studied separately, astronomers can compare their luminosities, temperatures, and spectra, while knowing that they almost certainly formed at the same time and from the same material. That shared history removes several unknowns. When two brown dwarfs have the same age but different masses, their present brightness becomes a direct test of how quickly substellar objects cool. When their measured masses disagree with model predictions, the difference can reveal missing physics in the treatment of clouds, convection, magnetic activity, or the interior equation of state. A binary is therefore more than two faint points. It is a small natural experiment assembled by gravity. Young clusters offer a related experiment on a larger scale. Members of a cluster are born within the same general episode of star formation. Their ages are not identical in every detail, but they are far more closely linked than unrelated objects scattered across the sky. By counting stars and brown dwarfs together, astronomers can estimate the distribution of birth masses. This distribution is one of the central records of star formation. It describes how often nature produces massive stars, sun-like stars, red dwarfs, brown dwarfs, and bodies near the planetary mass rangim. The smallest members are the hardest to measure, but they matter because they test how far fragmentation can proceed. A cloud does not choose a category in advance. Those structures gather material. Some become massive enough for hydrogen fusion, others do not. The final population is the visible remainder of turbulence, temperature, magnetic fields, radiation, accretion, and gravitational competition. The census is also shaped by time. A young, low-mass brown dwarf can be bright enough to detect in a nearby nursery. The same object, after billions of years, may cool into a faint T or Y dwarf and become far harder to find. Old populations are therefore hidden more effectively than young ones. This makes the galaxy seem to lose brown dwarfs even when it is losing sight of them. The coldest examples may remain undiscovered close to the Sun. They would not shine strongly, and their visible light could be negligible. Their presence would be revealed by weak infrared emission and by motion across repeated images. Distance becomes crucial. A cold object a few light years away may be measurable. The same object several times farther away can fall below the limits of a survey. For that reason, the local inventory grows not only through wider searches, but through longer ones. Years between images allow proper motion to accumulate. A point that once blended into the background begins to slide away from it. The solar neighborhood is not fixed. Stars and brown dwarfs pass one another on separate galactic orbits. Some nearby objects are approaching. Others are receding. Over tens of thousands of years, the list of our closest neighbors changes. A brown dwarf, now faint and distant, may once have passed nearer, carrying its unseen weather through a different part of the local sky. No ancient observer could have noticed it directly. There would have been no new star, no visible wandering light, no mark on a chart. Yet, the object would have been present, held in the same broad galactic current as the stars used for navigation. That unseen companionship changes the feeling of the neighborhood. The space between visible stars is not empty. It contains cold bodies, faint binaries, old remnants, dust, gas, and objects whose light reaches us mainly as heat. Brown dwarfs belong to that hidden architecture. They are not failed versions of the stars around them. In a census, they become evidence. Their numbers show how often gravity stops below fusion. Their pairings reveal which systems survive. Their missing close companions expose a boundary between formation routes. Their oldest members preserve the result of processes that occurred before the Sun had completed many of its journeys around the Milky Way. The galaxy builds on a continuum, but it does not build every mass in every place with equal ease. Brown dwarfs occupy that uneven middle, and by counting the faintest neighbors, astronomers begin to see the shape of the machinery that made them. Around some young brown dwarfs, the remaining material does not disappear at once. A disk can continue circling the central object after the surrounding cloud has thinned. Gas follows broad orbital paths. Dust grains collide, stick, break apart, and settle toward the disk's middle plane. The structure is smaller and less massive than many disks around young stars. But the basic ingredients can be familiar. This raises a natural question. Can planets form around an object that never became a star? The answer is not yet complete. Infrared observations have shown that disks are common around young brown dwarfs. Some display the same signs of accretion seen around young stars, with material still falling from the disk onto the central body. Radio telescopes have detected cool dust farther out, and in some cases that dust has already grown into grains, large enough to suggest that the first stages of planet building are underway. A grain only a millimeter wide may not sound important, but the dust inside a new disk begins much smaller, often as particles comparable to smoke. Reaching millimeter sizes means that collisions have allowed solid material to grow. It is an early step along a much longer path, one that may continue through pebbles, larger bodies, and perhaps objects massive enough to reshape the disk around them. Whether the process reaches full planets depends on how much material is available and how long the disk survives. Many brown dwarf disks appear to contain only a modest amount of dust and gas, and some may never have enough solid material to build more than small bodies. Others may have lost mass before astronomers observed them, and if planet formation began very early, part of the disk's original material may already be hidden inside objects too small or too close to the brown dwarf to detect. The absence of visible mass does not always mean nothing formed. It can also mean formation has already changed what the telescope is measuring. The smallest likely planets would be rocky or icy bodies, assembled from the disk's solids. Larger worlds would require either a heavier disk or a more efficient way of gathering material. Building a gas giant around a brown dwarf would be difficult in many systems because the disk itself may contain only a few Jupiter masses or considerably less. There is also very little time. Gas does not remain in a young disk forever. Radiation, outflows, accretion, and the surrounding environment gradually remove it. A forming world must build a solid core quickly if it is to capture a substantial atmosphere before the gas is gone. Small rocky planets may therefore be more plausible than giant ones in many brown dwarf systems. Yet even that expectation must remain flexible. Brown dwarfs form across a range of masses and environments. Their disks vary. Some are broad and relatively undisturbed. Others may be compact, truncated by encounters, or stripped by radiation from nearby stars. Each nursery provides different conditions. The central brown dwarf also changes rapidly compared with a true star. During youth, it may be warm and luminous from contraction. As it ages, its brightness declines. Any surrounding planet would receive less energy with time, even if its orbit remained unchanged. Around an ordinary star, the region where liquid water might be possible can remain at a broadly similar distance for very long periods. Around a cooling brown dwarf, that region moves steadily inward. A planet at one distance might begin too warm, later pass through temperatures compatible with liquid water, and eventually become too cold. Another planet closer in might enter that temperature range much later. This creates what researchers sometimes describe as a moving, habitable zone. The phrase requires care. Being located at the right temperature does not make a planet inhabited or even suitable for life. Atmosphere, pressure, chemistry, water inventory, magnetic environment, geology, and orbital history all matter. Around a brown dwarf, the early thermal history may be especially important. A young brown dwarf can be much brighter than it will become later. A planet that eventually reaches moderate temperatures may have spent its first era under stronger radiation. If it began with surface water, that water could have evaporated into the atmosphere. Ultraviolet light could then break some of the vapor apart, allowing hydrogen to escape into space. By the time the planet enters a cooler period, it may already have lost much of what habitability would require. This outcome is not unavoidable. A world could begin with a large water supply. Water might remain protected beneath ice, inside minerals, or below the surface. Later impacts could deliver volatile material. A dense atmosphere might redistribute heat and reduce some extremes. The details depend on circumstances that cannot be inferred from orbital distance alone. The orbit itself presents another condition. Because a brown dwarf is faint, a planet receiving meaningful warmth would need to circle close to it. At such distances, tidal forces could gradually synchronize the planet's rotation with its orbit. One side would remain turned toward the brown dwarf while the other faced away. This is called tidal locking. It is often imagined as a world divided between permanent day and permanent night, with one side scorched and the other frozen. Real atmospheres and oceans can soften that division. Winds can carry heat toward the dark hemisphere. Clouds can reflect radiation on the bright side. Ocean circulation can move energy across the surface. A tidally locked planet is not automatically lifeless. It is simply governed by a different climate pattern. Around a brown dwarf, the daylit side would not be illuminated like Earth beneath the sun. Much of the incoming energy could arrive in infrared wavelengths. The sky might appear dim to human eyes, even while the atmosphere and ground absorbed substantial heat. The central object would also loom large. A nearby brown dwarf could appear broader in the sky than the sun appears from Earth, depending on the orbit. Its visible glow might be deep red or barely perceptible, while its infrared radiation warmed the planet continuously from the same direction. The resulting climate could be stable in some ways and vulnerable in others. Brown dwarfs can possess strong magnetic fields. Some produce radio pulses, auroral emission, or energetic activity in their upper atmospheres. A close planet could interact with that magnetic environment, though the effects would depend on the brown dwarf's age, rotation, field strength, and the planet's own magnetic protection. The same interaction might erode an atmosphere under some conditions, or produce powerful auroras under others. At present, much of this remains theoretical, because small planets around brown dwarfs are exceptionally difficult to find. A planet passing in front of its host can block a noticeable fraction of the light because the brown dwarf itself is only about the width of Jupiter. In principle, this makes transits favorable, but brown dwarfs are faint. Their atmospheres can change in brightness as clouds rotate, and the closest planetary orbits may be short enough to demand repeated, carefully timed observations. A transit signal must be separated from weather on the object being eclipsed. Direct imaging presents another possibility at wider distances. A young planetary mass companion glow from its own formation heat and appear beside a brown dwarf. But when two faint objects share a system, mass alone may not reveal which one should be called the host and which one the companion. If a 15 Jupiter mass brown dwarf is orbited by a 5 Jupiter mass body, the smaller object may be called a planet, yet the pair may have formed together from cloud fragmentation, more like a very low mass binary than a planetary system. The names depend partly on origin, and origin is often the hardest property to recover. Nature leaves the final objects more clearly than it leaves the story of how they assembled. There may also be moons around free-floating brown dwarfs or planetary mass bodies. A disk surrounding a young substellar object could build satellites, much as the disk around young Jupiter is thought to have built its large moons. Such moons would orbit a body with no star nearby, would receive little outside light, but tidal heating or internal radioactivity might preserve warmth beneath the surface. No assumption of life is needed for these worlds to be interesting. They would show that planetary architecture does not require a shining sun at its center. Orbits, disks, collisions, tides, and chemistry can continue at smaller scales, lit mainly by stored heat and gravity. There is a present moment hidden inside that possibility. While you rest beneath a sky organized by one bright sun, somewhere in the galaxy, a small disk may be turning around an object too faint to see. Dust may be crossing the first uncertain steps toward becoming stone. A young moon may be gathering from a ring of material. A frozen world may be circling a brown dwarf whose warmth is already beginning to fade. None of these systems needs to resemble our own. Their value lies in how differently the same physical laws can arrange matter. A brown dwarf may never hold a lasting stellar flame, yet it can still become the center of a system. Gravity can gather companions around it. Disks can flatten, dust can grow, orbits can settle into repeating paths. The object that stopped before becoming a star may still have worlds, moods turning in its remaining light. The deeper value of brown dwarfs appears when they are placed beside other worlds. They occupy a useful middle ground. Their masses approach those of stars, while their atmospheres can resemble those of giant planets. They form warm and luminous, then cool through temperatures that overlap with directly imaged exoplanets, Jupiter, and eventually even colder bodies. Because many brown dwarfs travel alone, their light can be studied without the glare of a nearby star. That simple difference gives astronomers a clearer view of an atmosphere governed by many of the same processes found on giant exoplanets. Water vapor absorbs particular wavelengths. Carbon monoxide and methane respond to temperature and mixing. Clouds alter color and brightness. Gravity compresses the gas. Rotation organizes circulation. A distant planet may contain all of these features, but its host star can overwhelm the signal. With a brown dwarf, the atmosphere speaks for itself. A spectrum divides the object's light into wavelengths. Darker regions appear where molecules have absorbed energy, while brighter regions reveal atmospheric windows through which radiation escapes more easily. The resulting pattern acts like a chemical fingerprint, though it is rarely simple enough to read without careful modeling. Temperature influences every line and band, so does pressure. A molecule deep in a dense atmosphere may absorb light differently from the same molecule higher above. Clouds can conceal some layers, while exposing others. Disequilibrium chemistry can carry gases upward faster than reactions can transform them. Two atmospheres with similar temperatures can produce different spectra because their gravity, composition, and circulation are not the same. Astronomers build models that attempt to reproduce the observed light. They vary temperature profiles, molecular abundances, cloud thickness, particle size, gravity, and other properties. The models are then compared with measurements, sometimes across many infrared wavelengths at once. A good match does not create a photograph of the atmosphere. It offers a physically consistent explanation for the light that reached the telescope. Some properties remain entangled. A thicker cloud may resemble a cooler temperature. Lower gravity can imitate changes in composition. Unknown details of cloud particles can shift the inferred abundance of a gas. For this reason, the strongest conclusions often come from combining several kinds of evidence. Distance reveals luminosity. Repeated observations reveal rotation and weather. Binary motion reveals mass. Age estimates provide a cooling history. Spectra reveal chemistry and atmospheric structure. Each measurement removes part of the ambiguity left by the others. The James Webb Space Telescope has extended this work into wavelengths, where many brown dwarfs release much of their remaining energy. Its instruments can examine molecular absorption with a degree of sensitivity that earlier observatories could not reach, especially for faint and cold objects. Webb can observe water vapor, methane, carbon monoxide, carbon dioxide, and other atmospheric signatures across broad portions of the infrared spectrum. It can also study how clouds influence the light of young brown dwarfs and planetary mass objects. The aim is not simply to collect a longer list of molecules. The arrangement matters. A gas found in greater abundance than equilibrium chemistry predicts may reveal strong vertical mixing. A cloud feature may show where silicate grains remain suspended. Differences between two objects of similar temperature can expose the role of gravity or metallicity. Atmospheres become records of physical motion. One of the most demanding targets is Y0855, a nearby object whose atmosphere is colder than that of any other known brown dwarf. It releases almost all of its detectable energy in the infrared. Its temperature lies close to the conditions found among the giant planets of our own solar system. At such low temperatures, water may condense into clouds. Ammonia chemistry becomes more important. The familiar mineral clouds of warmer brown dwarfs have descended into layers too deep to dominate the visible atmosphere. The spectrum begins to resemble a bridge between substellar objects and cold planetary worlds. Studying such a body is difficult because faintness is the natural result of cooling. A cold brown dwarf is not hidden by great distance alone. It has very little heat left to release, even when it lies only a few light years away. Its signal can challenge the most sensitive instruments. Yet proximity allows the attempt. Y0855 moves across the background sky quickly enough to show that it belongs to the solar neighborhood. It is one of the nearest systems to the Sun, but it remained unknown until infrared surveys found its motion. There may be other cold neighbors still missing. Some could be fainter. Some may lie in crowded regions of the sky. Others may have colors that do not match the usual search criteria. Future surveys can discover them through combinations of motion, infrared brightness, and repeated observations over long intervals. The census will become a test of how brown dwarfs cool across the age of the galaxy. Old objects are especially important. Their low temperatures record billions of years of energy loss. If models predict that a brown dwarf of a certain mass and age should be brighter than it appears, something may be complete in the description of its clouds, interior, or atmosphere. The cooling itself becomes measurable physics. Young populations provide the opposite view. In nearby stellar nurseries, telescopes can look for brown dwarfs soon after formation, while disks and surrounding material are still present. Their brightness makes them easier to detect, but their low masses can be difficult to estimate because young objects have not yet settled into the slower, cooling behavior of old field brown dwarfs. Webb has begun identifying extremely low mass objects in regions where stars are forming. Some carry masses comparable to giant planets, yet they appear to have formed freely within a cloud rather than inside a planetary system. The distinction is important. A body can have planetary mass without being a planet in the usual formation sense. It may be the smallest product of star formation instead. Observations in the small Magellanic Cloud have also revealed candidates for young brown dwarfs beyond the Milky Way. If confirmed and studied further, these objects would allow astronomers to examine substellar formation in an environment with a different chemical history from the region around the Sun. That comparison reaches beyond classification. The early universe contained mostly hydrogen and helium, with heavier elements produced gradually by generations of stars. Modern molecular clouds contain dust, carbon, oxygen, silicon, iron, and many other materials inherited from earlier stellar lives. If brown dwarfs form in regions with fewer heavy elements, their numbers and properties can reveal how strongly the fragmentation of a cloud depends on chemistry and dust. A low metallicity environment may cool differently. Its disks may contain less solid material. Its atmospheres may form different clouds. The boundary between stars and brown dwarfs may remain governed by core physics, but the path leading objects toward that boundary can change with environment. For the first time, brown dwarfs can be studied not only as nearby curiosities, but as part of a broader history of star formation across galaxies. They also help prepare astronomers for the study of smaller and more Earth-like exoplanets. The instruments, models, and techniques developed for brown dwarfs teach researchers how to separate molecular signals, account for clouds, recognize chemical imbalance, and measure change over time. The objects are larger and warmer than Earth, but the interpretive challenge is related. Light passes through or rises from an atmosphere. Molecules alter it, clouds complicate it. The observer receives a spectrum and must work backward toward a physical world. Brown dwarfs offer many opportunities to test that process because their atmospheric signals are comparatively strong. When models fail, the failure can be examined without always confronting the added glare of a host star. They are practice grounds, but they are not merely substitutes for planets. Their interiors are shaped by stronger gravity. Their atmospheric pressures can be immense. Their weather is powered by heat escaping from below, rather than by sunlight falling from above. Their chemistry passes through states that ordinary stars never experience. They deserve to be understood on their own terms. There was a time when the category existed only because stellar theory predicted where fusion should stop. Now, brown dwarfs have become laboratories for cloud physics, magnetic activity, planetary atmospheres, binary formation, disk evolution, and the chemistry of cold worlds. The object once defined by what it could not become is increasingly studied for what only it can reveal. As telescopes continue to follow their infrared light, the boundary between stars and planets grows less like an empty divide. It becomes a landscape. Warm objects near the stellar edge glow through mineral clouds. Colder ones carry methane across rotating skies. The faintest hold water and ammonia in atmospheres approaching the temperatures of planets. Across that landscape, every brown dwarf marks a different moment in the release of inherited heat, and each one allows the galaxy's unfinished fires to be read a little more clearly. Every brown dwarf is moving toward a colder future. The change is not dramatic. There is no final burst, no sudden collapse, no moment when the object clearly becomes something new. Heat simply continues to leave. Energy rises from the compressed interior, crosses layers of dense hydrogen and helium, passes through clouds and molecules, and escapes into space as infrared light. Process slows with age, but it does not stop. Over billions of years, the brown dwarf becomes dimmer, cooler, and harder to distinguish from the space around it. Its mass remains nearly the same. Its gravity remains. Its rotation may continue for ages. What changes is the amount of warmth still stored inside. A young brown dwarf can glow at temperatures high enough to shape clouds from iron and silicate minerals. Later, methane becomes more visible. At lower temperatures, salts, sulfides, water, and ammonia can influence the atmosphere. Each stage is part of one long cooling sequence. The object does not pass through these conditions at a fixed rate. A massive brown dwarf can remain warm longer than a lighter one. A young low-mass object may briefly resemble an older, heavier body in temperature and brightness. Clouds can delay or redirect the escape of radiation. Composition can alter the chemistry of the atmosphere. Age, mass, and appearance remain woven together. This is why brown dwarfs are sometimes difficult to read from a single observation. Their present light is the combined result of how they formed, how heavy they became, what they contain, and how long they have been cooling. A spectrum gives one chapter of that history. Motion gives another. Gravity, when it can be measured through an orbit, gives another. Still, the full object is assembled from all of them. In the distant future, the brown dwarfs now known to astronomy will be colder than they are today. Their mineral clouds will sink far below the visible atmosphere. Methane and water will become more important. Some may develop layers resembling those of giant planets, though their stronger gravity and different origins will continue to set them apart. Eventually, many will radiate at temperatures too low for present instruments to detect across large distances. They will not disappear. They will simply become less luminous. The galaxy may already contain enormous numbers of such old bodies. Some could have formed during the early history of the Milky Way and cooled through nearly the entire age of the universe. Their heat would now be faint. Their light shifted deep into infrared wavelengths, their presence revealed only when they pass near enough for sensitive surveys to notice their motion. They may travel alone between stars. Others may remain in binaries, circling companions that have also cooled. Some may orbit long-lived red dwarfs. Some may hold planets or moons whose own histories unfolded under a dim central glow. Their systems will continue even as their light fades. Gravity does not require brightness. An orbit can persist around an object that produces almost no visible illumination. A moon can continue circling. A pair of brown dwarfs can complete one revolution after another. The structure remains after the original heat has become difficult to measure. This separates energy from presence. Human vision often treats brightness as a sign that something is there. The visible sky reinforces that habit. Stars announce themselves. Planets reflect sunlight. Nebulae appear where gas catches radiation from nearby sources. Brown dwarfs remind astronomy that much of the universe does not announce itself in visible light. Matter can be present without shining brightly. Weather can move under a darkened sky. Gravity can organize a system around a body the eye would never see. The first astronomers who searched for brown dwarfs were looking for a missing category. They expected there should be objects below the smallest stars, but the boundary seemed empty, because their instruments could not yet reach far enough into the infrared. Once the right detectors were built, the emptiness filled. The same pattern has appeared throughout astronomy. New wavelengths reveal objects that visible light concealed. Radio telescopes uncover cold gas and magnetic activity. X-ray observatories find matter heated to extreme temperatures. Infrared instruments look through dust and detect bodies whose warmth is too faint for ordinary sight. The universe does not become larger when a new instrument is used. Our access to it becomes wider. Brown dwarfs entered astronomy through that widening. They were not created by their discovery. They had been cooling between the stars long before anyone knew how to find them. Their atmospheres had already passed through clouds and chemical changes. Their magnetic fields had already sent particles through surrounding space. Their companions, where they existed, had already completed countless orbits. The telescope arrived late. That lateness is part of the perspective brown dwarfs offer. A human lifetime catches only a narrow interval in the cooling of one object. Even the history of astronomy covers almost none of it. What researchers observe is a population spread across different ages, each body providing a still frame from a process too long to watch from beginning to end. One brown dwarf is newly formed and warm. Another has cooled for hundreds of millions of years. Another carries the faint heat of a much older era. Placed together, they reveal a sequence that no single observer could remain alive to witness. This is how astronomy often studies deep time. It does not wait for one object to complete its evolution. It finds many objects at different stages and arranges them according to the physics connecting them. The method is imperfect. No two brown dwarfs are exactly alike. Their masses, compositions, clouds, and environments vary. Yet the population allows the long process to become visible. Birth in a collapsing cloud. A brief period of contraction, possible deuterium fusion. The failure to sustain ordinary hydrogen burning, the appearance of mineral clouds, the rise of methane, the movement toward colder atmospheric chemistry, the fading of infrared light. None of these stages is an error. They are the expected behavior of matter under a particular range of mass and pressure. The phrase failed star remains useful because it points toward the threshold brown dwarfs do not cross, but it can also narrow the view. It defines an entire class by comparing it with something else. A brown dwarf is not waiting to become a star. Its path was decided early, and it has been following that path ever since. It is a body supported partly by quantum pressure, releasing heat inherited from formation, carrying an atmosphere with clouds and winds, and sometimes organizing a system of companions around itself. There is no unfinished task inside it. There is only continuing change. In that sense, brown dwarfs make the boundary between stars and planets feel less like a dividing line and more like a region with its own character. At one edge, the smallest red stars maintain fusion for spans that exceed the current age of the cosmos. At the other, giant planets gather in disks around stars and reflect the light they receive. Between them are bodies that form like stars, resemble planets, and cool according to their own interior physics. The categories remain useful, but nature does not always arrange itself around the convenience of names. It forms objects from available matter. It compresses them. It allows some reactions and prevents others. Then it lets time continue. Far from Earth, a brown dwarf may be turning now beneath layers of cloud. One hemisphere moves into view while another rotates away. Heat rises through the atmosphere. Molecules absorb certain wavelengths. A weak infrared signal begins traveling outward. Years later, perhaps decades later, that signal may reach a detector. It will appear as a small measurement within a larger field of data. A point may brighten and fade. A spectrum may show water, methane, or carbon monoxide. Motion across older images may reveal that the object is nearby. From those traces, another hidden world will slowly become known. The brown dwarf itself will remain unaware of discovery. It will continue cooling as it has since formation, carrying no distinction between being observed and being alone. Beyond the reach of visible starlight, its last warmth keeps moving outward.